Alright, in the previous video we discussed forces, the types of forces. We have the force due to attraction, the force due to contact, and the force due to attachment. Now we are going to see the forces in play. And this will be the basic. This will actually be the basic of solving problems. So let's start off with equilibrium. And let's begin by discussing Newton's first law of motion. I'm doing this because this first law of motion, it implies equilibrium. First law of motion says every body remains in its state of rest, or motion. If a body is moving, it remains in that state of motion. If a body is at rest or it's not moving, like this one, like this pen is not moving, so it remains in its state of rest. So every body remains in its state of rest unless an external force acts on it for it to change that state. So basically, why did I say it's important? Because let's think about this. If a body is at rest, let's think of a body that is at rest. If a body is at rest or is moving with constant velocity, then there is no resultant force. We are going to explain on the resultant force. There's no resultant force acting on it, and any forces that do act must balance each other. That is what is called equilibrium. Equilibrium is a state where if any forces are acting, then they balance each other. They balance each other. They will have to balance each other out. This point basically means there will be no resultant. This is going to be very important when you're talking about equilibrium. Some of these concepts, they seem abstract now, but we are going to see on examples what this basically means when you say if any forces act, they balance each other in equilibrium, no resultant. You're going to see what that means. If something is moving, if the speed of a moving object changes, if something is moving, Newton's first law says it remains in its state of rest unless there is no. The better way of saying it is it remains in its state of rest of motion or motion if there is no resultant force. So if this state of rest or motion changes, it means there is a resultant. If it doesn't change, then there is no resultant. If it changes, there is a resultant force. So yeah. If direction is changing of a move, then there must be a resultant force. Basically, what that point means when I say if direction is changing, then there must be a resultant force. Direction cannot change because state of motion. If the motion is to the right, if this thing suddenly starts changing direction like this, what made it change direction? It means a force has been applied. Either it has been pulled in that direction, or it has been pushed. It has been pushed for it to change what? For it to change direction like that. Otherwise, it will not change. It will continue moving to the right like that if there was no resultant, which means there was now a force that wasn't balanced out. That's why it had to change direction. And whenever a force is not balanced, there will be a resultant force. So with no balancing out of forces, there is the existence of a resultant force. So let's get into examples. Let's get into examples for you to see this, for you to see this equilibrium concept at work. Let's take a simple example. My favorite example, a book on a table. Let's take a book on a table. If we put a book on the table, I don't think there are any books that have a mass of 6 kgs. Oh, that would be just too heavy. Yeah. So now let's take a stone block of 6 kgs. So the mass is equal to 6 kgs. The mass is equal to 6 kgs, right? Okay. So now, because this book is in a what? in the Earth's gravitational field, it will have a weight. And you know from Newton's second law of motion, the force is calculated as F is equal to ma. But the force is a special type of force called a weight. So the weight is equal to mass. But the acceleration is a special type of... This concept you are going to understand it better when you do gravitation, when you're now considering the force due to gravity. So the acceleration is now a special type of acceleration called g, or acceleration due to gravity. So let's calculate the weight of this stone block. We know that definitely it's going to have a weight because it's what? It's in a gravitational field. Let's calculate that one. It will be 6 times. We are going to use acceleration due to gravity, 10 meters per second squared. I'm going to use this because it's better for me to calculate well. So the weight is just going to be 60 newtons. I'm putting newtons because weight is a force. Force is the units newtons. So here the weight is what? Is 60 newtons. And then you are complaining, and then you complain to your friend. You complain to your friend that no, you cannot what? You cannot push this on your own. You need his help. He's the stronger one. So you ask him, friend, may you help me push this stone? The friend decides to what? To pull it. The friend pulls it with a force of 5 newtons. But we said there is a contact force. Another contact force that we left out here is called what? It's called reaction. So we are going to have a reaction force like that. We are going to have a reaction force facing up like that. But as this friend tries to pull this block, there is a force that opposes that motion, that doesn't want this block to move. That force is the force of friction. It doesn't want this block to move. So we are going to call the force of friction F. So this is the situation. This block is not moving. Let's think of a situation where this block is not moving. It's remaining in its state of rest. What does state of rest imply? It implies there is no resultant force. No resultant force implies what? The forces are balancing each other out. So what does that mean? It means what is pulling to the right is equal to what is pulling to the left. What is pulling downwards is equal to what is pulling upwards. For them to neutralize. Otherwise, if they didn't neutralize, this stone block was going to move. So basically, for equilibrium to exist, or for the conditions of equilibrium to hold, it means forces to the right should be equal to forces to the left. Isn't it? Should be equal to forces to the left. Otherwise, if they were not equal, then there would be a resultant force. They would not balance each other out, and this thing would move, but it's not moving. So which means forces pulling to the right are equal to forces pulling to the left. I know most of you have played tug of war once in your life. So this is just tug of war forces. These forces are playing tug of war right in front of our eyes. This one is pulling to the right, this one is pulling to the left. But they are neutralizing each other because this thing is not moving. If it was moving to the right, then this 5 newtons would have been greater than this F. But it's not moving, so which means this 5 newtons is exactly equal to F. So forces to the right, 5 newtons, are equal to forces to the left, which is F. Therefore, my F is equal to 5 newtons. Same thing applies. Let's say there's a vertical tug of war. The weight is pulling it down. But because this object is not sinking inside the table, and also it's not flying off the table. It's remaining in its state of rest on the table. It's not sinking. It's not flying. It basically means the forces pulling it downwards should be equal to the forces pulling it upwards. Otherwise, one of these directions was going to win the tug of war. So which means forces up should be equal to forces down. So what are the forces pulling up? The reaction force is pulling up. So my R should be equal to the forces pulling down, which is equal to 60 newtons. 60 newtons. Simple as that. We have solved for our F and our R. Let's move on to the second example. This one I'm just going to do it quick, but I'm just going to do this one quick because already the concepts are the same that we applied here. So let's get on to that one. a particle of weight 70 newtons hanging at the end of a vertical string. So we have a particle hanging at the what? End of a vertical string, and we are already told its weight. We are told that W is equal to 70 newtons. Is moving up. They're saying it's moving up with a constant velocity. This one is a very interesting example because this thing is no longer at rest, like this. But don't think it's at all different from equilibrium or anything. It's not really different. There is no equilibrium because this thing is okay. There is actually equilibrium, but we're just going to see where equilibrium comes in. I'd like that to say there's no equilibrium. There's actually equilibrium. Why am I saying there's equilibrium? Our equilibrium condition says what? The body should remain in its state of rest or should maintain its state of motion. The state of motion should not change. If it's moving, it should remain in its state of motion. This question says this body is moving with constant velocity, which is our keyword. Constant. Constant means no change. No change means the state of motion is being maintained. When state of motion is being maintained, we are back to what? To equilibrium. We are back to equilibrium. So in this case, although it's moving, but it's moving at a constant velocity, it's maintaining its state of motion. State of motion is only maintained when what? When there is equilibrium. So which means the forces that are pulling up, we know that there's a string and our tension acts along the string. So the tension is the force that is pulling it up. The weight will always pull it down. So we know that since there's equilibrium, the forces pulling up are equal to the forces pulling down for them to what? To neutralize and maintain the state of motion. Therefore, our T, which is pulling up, is equal to what is pulling down, which is what? 70 newtons the weight. So this is example number 2 for when the body is actually experiencing a state of it is a state of motion. So now let's look at another example. Example number 3. I'm sorry if I'm rushing, but I just want to finish this before the 30 minutes time. So now let's do this one. But no, I don't think I'll be able to finish this because it's introducing a new concept that will be interesting for us to discuss. So I think I'll do this in the next video. I think we'll be left with only 2 examples. The notes, I'll upload the notes, the PDF version of the notes, and you'll see other examples that we cannot go through in this video. So stay tuned for the next video. We'll only do one more example. Thank you.